So now I have to admit this is my first moderation of a hybrid meeting, so if I don't know where to look, please excuse me. I will still do my best. So as mentioned, the workshop is now on sustainability and circularity, which are two keywords, that cover, I believe, all and everything that we need to do. We need to be sustainable, and we need to reduce our use of resources. It's actually one of the like we all work in the energy field, so we know about renewable energies and the fossil energies, but like the day in the year where we have used all our reusable or renewable resources, all of it, including energy, is moving forward. I think it's now down to May. This is really critical. So we are not only using too much energy, but we are using too much of, let me call it, everything. And so this is what leads us also to the concept of circularity. We need to stop that. We need to stop that very fast. For the workshop, so to generate zero carbon energy cost effectively is necessary, but it is not enough. In a finite world, renewable energy technologies must also be made from safe and recoverable materials, and where possible offer environmental co-benefits, and we don't need to use too much, as I just mentioned. So in the following, you will hear, hopefully, 6 presentations, both online and in presence here in Limerick, providing current status and future perspectives in the research and energy fields on these matters, sustainability and circularity, given by members of the EUREC network. It is now my pleasure to invite our first speaker, Laura Martinez from CENER, our EUREC member in Spain. And now we'll talk about EU trends in sustainability concepts and hear the experience from CENER. Please, Laura, so I will disappear and then come back. You have a bit less than 15 minutes and a few minutes for questions.
Okay, so thank you very much. Okay, so thank you very much. Firstly, for the invitation to do this presentation to EUREC partners and also our hosts today. My name is Corcuera. I come from the National Renewable Energy Centre in Spain, and I want to, with this presentation, I want to give an overview of the EU trends and sustainability concept, or at least how we understand these trends are coming. Right, we are a research centre in a small town in Spain. We are about 200 employees, mainly PhDs and engineers, and we focus on 5 or 6 or 5 technical verticals in energy, both onshore and offshore, photovoltaic solar energy, solar thermal and thermal energy storage. We also deal with how to integrate the renewables inside the grid and how to manage that, but also with the storage. We have a department of energy in buildings, thinking on how to integrate renewable energy in the building, in the neighborhood, in the district, and in the city. And last but not least, our biomass department focus on biofuels and waste management. So let's have a little bit of context, right? So climate change is coming, it's not new. We've been warned from several decades, but I don't know if you feel like me, like this little man in the picture, that it's in the last decade when we are seeing really policy movements and really policy actions towards this climate change, right? So today's workshop is about circularity and sustainability. I want to, because I'm the first one, so define a little bit what circularity and what sustainability is. No? Circularity, according to the Circular Economy Action Plan, is to provide high quality, functional and safe products which are efficient and affordable, last longer, and are designed for reuse, repair and high quality recycling. So what the Circular Economy Action Plan is asking us to do is to change completely the paradigm of the linear economy that we are having right now. Now we take a raw material, we transform it, we use it, and then we waste it, and that's it, right? So we need to very completely this line, and this the European Commission is suggesting a plan on how to do this, and we need to approach all the different steps of the plan to make it really, really circular, that circular economy and that circular growth. So this plan is bringing to the state of play that we need to reduce the amount of resources that we need to do the same things. We need to rethink the items, the products, the technologies that we are developing to make them sustainable, to make them use less energy, to make them recyclable. Then we also have the consumption and the use of what we are creating, right? So there's a new concept to bring in, like the right to repair what we've already bought, or use less things to do the same. And at the end, the recycling and the reuse phase, this circular plan is asking us to reduce our wastes, but also to rethink our wastes, because this waste can be a raw material for another cycle again. So this is circular economy. Circularity is not recycling, as maybe some can think, and it's about the shift in an economy concept. However, sustainability is not only circular. Sustainability has been defined to satisfy the present needs. Something sustainable or sustainable growth is when we satisfy the present needs without compromising next generation future, which is a much broader and holistic approach of growth, right? So the sustainable growth should be inclusive, resilient for the humans, and resilient for the planet. And we can only achieve this if we are gaining a balance between industry, environment, climate, and also energy policy. So sustainability, sustainable growth is a holistic approach where we need to consider climate and environmental protection, economic growth, efficient industry. We need to reduce poverty. We need to look at the cities, the social inclusion, the biodiversity, and of course the circularity. So it's a much wider concept. Bringing a little bit of policy context to this, we start hearing about sustainability in the Juncker plan. He started with this sustainable growth in order to develop an economy based on knowledge and innovation, but resilient and green and resource efficient, and social issues started to come to state of play. And now, in the current presidency, with our President von der Leyen strategy, we have this Green Deal that is changing almost everything in the policy right now. And recently, well, we also have the recovery plan for Europe after the COVID crisis, and well, now in the news, the Repower EU plan. So, key milestones for us. In 2015, we have the Sustainable Development Goals, which were boosted by the United Nations, and it was where firstly sustainable was defined in this holistic way. There was an international agreement on this, and many countries signed and decided to approach to the sustainable goals. Europe signed this agreement as a bloc and wanted to take the lead on this. And this is where sustainable world, where the word started to enter the legislative papers for this time after this sustainable development goals. Then in the same year we have the Paris Agreement, which was also a great milestone, where again internationally there was a commitment to reduce greenhouse emissions and to stop global warming at least less than 2 degrees, if possible 1.5 degrees, and we'll see. And also in the same year we have the Energy Union, which was one cornerstone of the Juncker plan. They wanted to create this energy union plan with this vision to have a secure, sustainable and competitive and affordable energy for all Europeans. So again, sustainable and energy start coming together at that time, right? So, well, with this energy union appeared the set plan, which was the plan to boost the investment in low carbon technologies. Then from 2016 to 2018, there was the first legislative package called Clean Energy for All Europeans, named also as the Winter Package. So there was a set of regulations in order to reduce greenhouse gas emissions and also to improve and boost energy efficiency. And well, in 2019, our great character, the most emblematic policy these days, which is the Green Deal, right? So the Green Deal, with the arrival of von der Leyen president, wanted to transform the EU economy to be modern, efficient in resources and competitive, and with three main building blocks, which are net zero emissions by 2050, economic growth, important, detached of the resource use, and nowhere will be left behind. And after this Green Deal, plenty of strategies, many strategies, sectorial strategies appeared during 2020. Just to mention some, the circular economy action plan I've already mentioned, biodiversity strategy, farm to fork, offshore renewable strategy, hydrogen strategy, energy system integration. Okay, all these strategies that we need to learn by heart to focus our development, right? Early days, July 2021, the Fit for 55, which is called also like the delivering of the Green Deal, it's also called like this. So it increases a lot more the climate objectives, raising up to reaching less than 55% of greenhouse gas emissions by 2030, and also revises the Renewable Energies Directive and increases the need of including the energy mix up to 40% of renewable energies. And well, almost yesterday, May 2022, Repower EU, answering to the energy crisis that we are facing now, it rises again the objectives of the European Commission and the European Union to reach up to 45% of renewable energy in the energy mix by 2030, and also it is boosting the hydrogen as a vehicle for this energy transition. And if we are talking about sustainability, we need to get some words about taxonomy, which are driving crazy the industry and many of us, right? So the EU taxonomy is a science-based classification system, mainly to divide in what is sustainable or green and what is not, which economic activities can be funded, either private or public funding, and can be considered sustainable and green. So there are 6 environmental objectives in the EU taxonomy, and for an activity to be considered sustainable, they need to follow 4 criteria, which are to meet one of these 6 goals, one of these 6 objectives, to do not create any significant harm to the environment, do not create negative social impact, and also to follow the strategy of an EU technical expert group. So let's move on now to a little bit, let's check my time, okay, 11. Now I want to show some numbers, just very quick, on how sustainability has been funded in the EU funding programs. So in the, So in this graph up here, you can see how the funding for sustainability, as it is, has been evolving over the years. So now you can see here in 2021, 2022, with the opening of the Horizon Europe program, funds for sustainability development increased a lot. You can see here, red is Horizon 2020, this is the Green Deal last calls, and but this dark blue is Horizon 2020. But I want also to, can you see it in Greece? Right? But what I wanted also to pinpoint is, like, if we remove from this graph Horizon 2020 and Horizon Europe, which is the graph below, you would see that, well, in this years, we have sustainability is entering in many different funding programs that not only the ones devoted to research and development. So you can see here, okay, Eurostars, but also LIFE program, which is obvious, they are now talking about sustainability, but also the digital programs, also even Creative Europe, also the agriculture. So just there are going to be many opportunities to fund actions in different programs. I want to move because I'm running out of time, just to show you very quick how the sustainability and wind energy has been funded in the past years, and also, well, there's going to be many opportunities for the next years, 2021. Let's see what's going to happen, how it's going to be the trend for the next program. Well, just to finalize, I want to share with you that in CENER we've had about 29 EU projects dealing with renewable energies and sustainability. I want to just give some words about this flagship project, which is the European project about wind energy with the highest funding that ever happened, which is devoted to develop the offshore wind technologies, but look at here, always with this sustainable approach, which is to reduce also from the very beginning, from the design, to reduce environmental impact and increase social acceptance from the very beginning, from the development of the technology. Here we have this project led by us, coordinated by us, funded in the Green Deal past call, in order to develop seasonal storage technologies based on thermochemical energy storage and ORC technologies. We are also part of this Open Lab huge project with 33 partners led by Vito, which wants to create open innovation living labs for positive energy districts and sustainable energy management in the neighborhood scale, which is in the territory, in a little community scale. And while this is a typical biomass and circular economy, classical circular economy project, we have a waste, which is the olive leaves after olive growing, and then due to biorefining technologies, we get further high-value products. And last but not least, also funded not only by Horizon Europe or Horizon 2020 projects, we are receiving funds from the Resilience and Recovery Plan, and also from the REACT EU funding to create a new laboratory for development of advanced biofuels in order to provide technologies to decarbonize those sectors that are difficult to decarbonize, like heavy transport, shipping, and just the very end, very last slide, the take-home message for me would be that, well, me, myself, and I, we've created the problem if we look at the world in that way. So, but now the opportunity is that if we switch minds and we act as we can face this global warming. Thank you very much.
Yeah, many thanks, Lava. I think we need to group around this one microphone. That's the bigger group. Many thanks for the presentation. The floor is open for questions to Lara.
Yeah, one question about taxonomy of the EU. There are 6 items on which they make their decisions on granting. But this is also as usual. What are the
Honestly, I we're watching now is that, for example, programs in the destinations, in the impacts that we have to read and fulfill, for example, in European projects, we see that these 6 objectives are already there. They don't call it taxonomy, but they are already there. And they are not going to find any project that's going to cause any significant harm to the environment. They are asking proposals to explain if the technology is going to cause a harm or is going to be, not to go focus on circular economy. So we need to explain if we are not fulfilling this. It's written in the proposal that you have to explain that. So I don't know if there's going to be a taxonomy for circularity. I don't know. What we have is this one, and it's already inside the work programs and the destination and the impacts that the European Commission wants to fund.
Any further questions? So thank you very much. Thank you very much, Lara, for this nice overview on several terms on new level. In fact, the taxonomy did create quite some discussions, including the gas focus and nuclear. Okay. I did forget to introduce myself also to the online community. So my name is Rainer Janssen. I'm Managing Director Project of EUREC Renewable Energy Centre, a consultancy based in Munich. And I'm also currently Eurac President. And I'm now taking the opportunity to have a slight change in the program. I will introduce our Eurac Vice President as the next speaker. Wolfram Sparber will join us via Teams. Wolfram is leading the Eurac Research Centre based in Bolzano in northern Italy. And Wolfram will be talking about supporting the circular economy on a regional scale. So basically how to apply this concept of circular economy regionally. Now Wolfram, I'm not quite sure where you're coming in, so I will say.
Hello, good morning to all. Can you hear me?
Yes.
Excellent. So I will share my presentation. I cannot see you, but I hope you see me.
And Wolfram, 15 minutes plus a few questions, okay?
Yeah, I will be shorter. So so thanks for the invitation and the possibility to share our small experience about this aspect. So we are mainly working in renewable energies and energy efficiency, but started lately as well with some activities in the field of life cycle assessment, because especially in the building sector it becomes more and more an issue, and connected to this as well in the field of circular economy. So what I'm presenting you now is very shortly an overview of a project which we have done on request of the Italian Ministry of Environment with regard to circular economy in South Tyrol. So this is an English translation of the main results of it. So the presentation has been done by my colleague Joanna Bastos. She's an NCA expert, and I'm basically just reporting or bringing attention to where our experiences in the field. So obviously circular economy, I imagine that is widely known, so I will be very short on this. So the idea on the regional level especially is to understand how much more can be used the waste which we produce at a regional level. So on hand sourcing the first time materials on a regional level, on the other hand try to rebring into the search of new products what is waste from older products. So this obviously is a matter of closing the loop in sense of building the materials or the products in such a way that at the end of lifetime they can be brought back and possibly reused as fast as possible. And that means if we talk about a construction material and construction site, what is our topic here, mainly as well to have the possibility to get the single materials out of a composite wall. So if you're talking about walls, how can you separate the single components, the single materials which are in that wall, and how can you separate them in a clean way, you know, that the materials then singularly the possibility to bring it back to new construction. So we are basically trying to decrease the volume of waste that we produce, to slow down and to close the loops of the flow, so to bring back the materials, to bring back the resources, and with this to lower the need of new resources which we're bringing into the construction. So in our example, what we had a close look at were 4 types of flows with the objective of having a look at the possibility of reducing the material input and output. So mainly forests on the one hand, so wood-based product. On the other hand, agriculture, so co-products of waste. Have a look at the built environment and see what and how this might come back, and is the waste at the moment in our situation. So basically what we did is a GIS analysis of where the materials is now being, let's say, produced. On the one hand, the biomass waste material from agriculture. On the other hand, the biomass raw material, which we take out of forests, and when you see several maps showing mainly where this activity is being brought and how much material is being done. Because especially if the material is of low value, high volume, a big issue is the matter of transportation, the cost of transportation. So how far do you have to transport that material in order to bring it back? And can you do a business case out of that? So then we went into more details in order to analyze the millions of kilograms which are used in the single material. So, for example, cement and construction materials, or minerals, or biomass-based activities, and how much is the input and how much is the output of this single material in different time frames. So we had a look forward and tried to estimate what is going to be the construction site in future, and basically starting from the points right now. And what we saw from the models using literature-based coefficient of construction, that actually the estimates much lower, as what we see is the real generated construction emission waste in South Tyrol, which is relevantly higher. So for some reasons which are not very clear to me right now, basically the literature paragraphs and the real data, there's quite a big, let's say, mismatch or not alignment in these activities, but nevertheless it shows the relevance about the activities, because we are still talking about 1 million tons a year of demolition material. Although South Tyrol is an area where there's quite a lot of construction going on, and it's mainly, let's say, enhancement of existing buildings or adding of new buildings. So I would say we have not a strong focus of demolition or reduction of materials. So, okay. Then we tried to make a comparison of polystyrene of EPS as a widely used isolation material, and wood fiber as a isolation material where wood fiber could be produced using local wood, and how this would look like with regard to greenhouse gas emissions, and as well independence of where it comes from. In our cases, we are a border region between Italy and Austria. It might come directly from Italy, or it might come from Austria. So here again, we used eco-invent data with regard to this LCA estimation materials, and then we had a look at how could be the possibility, or how much is the need, let's say, on a local level, the possibility to use local wood. And if you look on the right side, starting gas-powered gas data, what we see basically is taking together agriculture and biomass use, and we would take out of 50% of this. This would result in around 318,000 tons of wood fiber insulation, and the need the annual building requirement for residential buildings is around 6,400 tons. So basically, assuming a replacement of this amount of EPS, we would need about 31,000 tons, which is around 10% of the volume of the residual biomass, which is actually a data which is in line with what we could isolate. So this is basically a very preliminary analysis in order to show potential and to sensibilize. What we did in the project as well is go deeper in these figures, but especially to start to set up a concept of an online database where companies can register and show on the one hand their needs and on the other hand their waste. This is needed in order to start basically a material direct bilateral material flow. On the other hand, what we saw in interacting with several companies is that the topic is quite sensitive, and companies tend not to want to show and to share this data. So this is an issue which has to be overcome in the sense that obviously if you don't show the data of the materials that you need, of the waste that you have, it is difficult for other companies to see if there's a potential and a link in interacting. So this was an aspect that we discussed more widely, and I'm curious to see, because if you discuss with companies and to the local authorities, there's a big wish to enhance the circular economy aspect, but on the other hand, if you get into concrete proposals and offers, you see that the implementation is very difficult. So I just wanted to share this experience with you. The reports are available, unfortunately, only in Italian and in German. But obviously, if you have any further questions, we are available, or I'm happy as well to forward it to my colleagues and come back to you in the next couple of days. Thank you very much, and I'm handing back to Ryan.
Many thanks, Wolfram. Everything worked well. I hope also your telephone call is working. So greetings to Liberty. Are there any questions from the audience? Wolfram, just from a quick question from my side. You were saying that the industries they acknowledge the problem, but they prefer not to move in the moment. What do you believe would could be done, or maybe it's from your expertise in what needs to be done basically to take the first steps? I think this is the question you can ask on almost all topics.
So obviously it's only a thought from my side, but maybe other participants here have complete experience. What we try to discuss with them, and there seems to be a certain openness, but how much it is accepted has also to be seen, is the fact that you open the platform only to actors which are willing to share their own data. So basically that you might open the platform for everybody, only in a cumulative way, so that you can get summarized data, but without seeing in precise where how much material is available, but only that you see the overall sum of the companies who have registered what kind of materials they have, without knowing which company is giving a disclosure of which material. And if you want to see more detailed data, you have to be willing to share your data. So then you see somehow it is a closed club, and the ones who are in are seeing, but are as well sharing. And if you're not sharing, you're not able to see. Obviously, the difficulty is that there are some companies which have a lot of materials to give, and other companies which have a lot of material that they need. And there's the higher sensibility of the companies who give to share data than the ones who need, because that is more of a public knowledge, in the sense that if you know that a certain company has, I don't know, 5 construction sites in front of them, you can estimate the volume of the building, and therefore you can estimate the volume of the construction material. While the other side is more critical. But the real implementation, we are not yet there.
Many thanks, Wolfram. So, Wolfram, as there are no further questions, also not from the chat, that was a pleasure meeting you again, and have a safe trip back until soon.
Thank you very much, and I wish you all as well a good continuation of the workshop and a good trip back.
Thank you, Wolfram.
Thank you.
Michael will talk about the title of his talk is Bigger, Smarter, Circular, Wind Energy Research at the Federal Republic of Germany's Research Center for Aeronautics and Space, and that is the DLR. Michael, it's your program in the Bigger, Smarter, and Circular. Yeah.
How do they want to make it?
Good morning, everyone. Thank you so much for having me. Also, good morning to those participating online. My name is Michael Kreuz. I'm not on the slides. It's good goes to those on the slides who prepared the presentation. Some of them might be joining us online. I'm not quite sure. But yeah, thanks anyway for having me. Thank you, Laura. You perfectly sort of seen. Which allows me to jump right into the topic, which is today wind energy research at the DLR. To start off with, I'm going to give you a few snapshots at what we're doing at DLR in the field of wind energy research. As I said, a few snapshots, a few pictures. Just some nice ones to look at. This is our assembly hall. It's close to Hamburg, so it's in another part of Germany. What we're doing there, we are producing smart plates. On this slide, you can see some 20 meters plates that we are producing, actually manufacturing together with colleagues from both Fraunhofer and partners in the US. So they are produced in Hamburg, as I said, and then they were shipped to the Fraunhofer facility for testing, and some more were shipped to the US to our partner Enrel to do some further testing. Segmented rotoplates is one of the topics that is of great importance to us, and we're kind of, I wouldn't say proud, but to some extent we're kind of proud to hold some patents on how these segmented blades can be coupled and decoupled after a while, and I was told by the colleagues that this is something I wouldn't say unique, but it's kind of unique, and that the guys are rather proud of. It's not just for transportation issues, so it makes porous transportation for the blades easier if they are decoupled, but it's also, I was told, for efficiency issues. Then trailing edge flat. This is also some nice example of what we at DLR are doing in terms of synergies. So this, as I said, this example shows synergies between the aviation geeks and the energy geeks. So of course, when it comes to this edge flaps, it's all about aerodynamics. So this is, I think the picture was taken in Braunschweig, where we have some big aviation institutes there, and then this is upcoming, so to say, our research wind farm is going to be built. So we are in the building process, and those of you who are familiar with infrastructure planning and infrastructure implementation in Germany, they might know that everything we do in terms of infrastructure takes a while in Germany nowadays. But we are in the process. This is just an illustration, so this is not exactly how it looks like, or how it will look like at the end of the day. It's going to happen, as I said, close to Hamburg. We're going to make use of Enercon E150 turbines, some of them, and then some smaller customized turbine. The overall goal, and this is pretty much what we intend to do with this research wind farm, is to better understand the wind, its pattern, its impact on different turbines that are close to each other, standing behind to each other. And I was told that this is another example of close collaboration, not only with different research institutes such as Fraunhofer and others, or Emerald in the US, could also serve as a brilliant platform to include industry and to enhance our role of technology enabler for further industrial application. So this is in a nutshell, and shown with a few fancy slides what we're doing in the field of wind research at the ARC. These are some more pictures, and now we're moving into the field of waste and waste generation. This is a colleague of mine who's doing his job there, and yeah, there's this picture there, and you can see that we have all the glass fibers, the plastic there, which is rather hard to recycle. That's an issue, and this is pretty much the motivation for our talk this morning. Here you can see, this is the full screen, some waste proposals. As you can easily see, this is a German source, the Umweltbundesamt. So this is valid for Germany only, and then the point is not going to deep into the curves there, and then there will be some more expertise in the room to easily elaborate better than I do on the fibers and the ups and downs. But what you see there is at least some kind of the German attitude towards wind energy and wind parks. So it goes up and down, and depending on how many of wind rotors we build and how many of them needs to be refurbished and reused, and how much waste is going to be produced. So let's switch into the concept for circular economy, and what I want to do is to bring the two sides of the coin together. So the wind activities and then the concept for circular economy, and this is no big DLR invention. This is just some systematic approach that we follow. I'm going to go through the slide in a second. I mean, the left-hand side, it's rather easy to understand. So there is, of course, the idea of prevention, so we do nothing. But there is nothing to recycle at the end of the day. But then there is the step of reusing, recycling, recovery, and disposal, which we try to avoid, of course. As this is rather, theory, and I do, even the Russian bubble, I do prefer to show concrete examples. I go through this slide just to give you an idea of what we're doing. So we've got the wind turbines there. And then we start. It's shown in the upper right-hand side. It's hard to see. I'm sorry for that. We go through, the whole cycle, starting from the rethinking and reusing stuff, and then there's this concept of disassembly steps. So what you can see here on the R3, R4, R5. So what we're doing in this step is to monitor closely, to see what is happening, to know the materials, to know the location, to have knowledge on the stress, on the damage, to then evaluate whether they can be reused, whether they have to be refurbished, whether it's what we, at the end of the day, efficient, that the parts are refurbished, or whether they need to be, can be reused, or whether the end of first cycle is achieved. What I like most on the slide, to be honest, is this R6, R7. So the idea of using materials, using components for a different application. So what you can see right there is the repurposing of intact structural parts and use them for this off-grid housing, which I feel is yeah, rather nice concept. And then further down the line, there's more ideas, there's more stuff that we do or intend to do in the near future about recycling of long fibers, about degradation, and further recycling steps. And at the end of the presentation, just in case this is going, here we are. This is a picture that has been shown by Laura in a similar aspect. So you were talking about circularity, you were talking about the whole circle, and as I'm Brussels based, there's this picture of this life cycle assessment that must not be missed in the cross bubble. So I'm happy to share this last slide to you. And in case of any questions, as I said, with you guys, maybe some of them are online. We're happy to take any questions and I'm happy to get into contact with you. Thank you so much.
Many thanks, Michael, and a very nice presentation. Are there any? It does show that we will continue further discussion with our colleagues from Alan, Weekend and the Alan. So there might be opportunities for cooperation. But are there any questions?
Yeah, thanks, Michael. I was going to ask you about the smart blades. Is there any one particular thing about smart blades? Circularity.
You asked my personal opinion. I think it's both. I think it's both. Of course, it is the efficiency aspect, which why it's called smart blades and blades. But what I learned, in the preparation of this talk, what I learned from my colleagues, that the designing process and the materials that we use are I don't know.
Just
invite Dominic Eber from EUREC Catapult from close to Newcastle in the UK to talk about sustainability and circularity from weak turbine blades to local energy communities. Paul, it's the floor.
Okay, thanks, Ryan, and good everybody, both here and online. So as Ryan said, I'm going to talk about sustainability and circularity. I'll give you a couple of examples. Firstly, with wind turbine blades and also local energy communities. Just move this on. Okay, so before I get into the detail, I was going to give you a bigger picture about how the future energy system is transitioning from a UK perspective, and also explain a little bit about the sort of increasing role we think that hydrogen is going to play, and that's very much playing into the sustainability element of the future energy system. Then I'm going to move more into circularity with wind turbine blades, and we've heard already from our previous speakers some of the key points which hopefully I will complement and add to. And so I've got a view from EUREC Wind, which is a European organisation, and also some activity that Catapult are involved in at the moment. And then finally, I'm going to move back to more sustainability considerations with some of the local energy system projects that we're involved in. So this slide here is trying to summarise how the UK energy system is transitioning or transforming at the moment. So just a couple of highlights. We've currently got about 11 gigawatts of offshore wind in the UK. Most of our homes are heated with gas, and most of our vehicles are fuel engines or internal combustion engines. And then in terms of the future energy system, some of the things that we're trying to do is really push on renewables, particularly offshore renewables in the UK. So we have a 2030 target, but what that long ago wasn't, I think it was 30 gigawatts last year, and then it became 40 gigawatts, and now it's 50 gigawatts. So we're really pushing the boundaries in the UK for offshore wind in what will be 8 years' time. We're also trying to wean ourselves off gas in domestic applications, obviously push the number of electric vehicles, and also reduce the amount of electricity generation comes from fossil fuels. So these will be aspects that will be familiar to many countries that represent in this room. What it means in terms of outcomes is offshore wind deployment will be much bigger than what we have at the moment. So going out to 2050, we're looking at 80 gigawatts, potentially 100 gigawatts of offshore wind in the UK. And then also we're reasonably confident that the variability of renewables, which is often seen as an Achilles heel, will be largely overcome as we tackle the storage technologies and interconnection of different systems. So in a nutshell, the future energy system in the UK and other countries, as I was saying, will be more decentralised. It will be multi-vector as well, and it will be reliant on renewables. And from a UK perspective, that reliance on renewables means offshore wind. That's going to be the dominant renewables energy source in the UK. And as I say, 50 gigawatts by 2030 is a realistic target. On the left-hand side of the slide, there's an illustration of the Dogger Bank wind farm, which is basically in process of being constructed now. So that's going to be one of the wind farms that will contribute towards the 2030 target. That wind farm in its own right is 3.6 gigawatts, so that's almost a third of what's operating in the UK waters at the moment. So it's a massive project, and it just shows you the scale of what's required as we move towards 2030 and then on to 2050. And related to this is the role of hydrogen. So about 18 months ago, the EUREC Capital were involved in a report that's on the left there, Solving the Integration Challenge. It was delivered as part of the UK sector deal, and it's its goal was to try and identify those opportunities for strengthening offshore wind. And what we, two of the big conclusions that are on the slide. Firstly, if we're serious about getting 50 gigawatts by 2030, 100 gigawatts by 2050, you're not going to connect all of that to the electrical grid. It's just not realistic. It takes too long to get the electrical infrastructure in place. It's difficult to do it in certain places. So we're going to be reliant on other energy vectors to get that amount of offshore wind into the energy system. And the energy vector that's most promising at the moment to work alongside the electricity grid is hydrogen. And then we're talking about different sorts of hydrogen. So, I mean, I've seen a few presentations in the last year or so, and there's a full rainbow colour of different types of hydrogen. What we focused on was green and blue hydrogen. So green hydrogen is obviously hydrogen that's from renewables, so offshore wind, for example. And then blue hydrogen is generally created from oil and gas sources. One of the issues at the time when we did this report was the cost of green hydrogen is much higher than blue hydrogen, but we're confident we can bring this down towards 2050. And given the current energy crisis that we've seen in the last few months, these numbers have definitely changed, and I would say it was more favourable towards green hydrogen. So you probably find that crossover point is sooner than what's illustrated here. So I would certainly advocate that green hydrogen is the way to go. So moving on to blades. So just over 2.5 years ago, EUREC Wind, which is the technology innovation platform with wind energy industry and research community representatives, they published a brochure in effect, which is all about how wind is going circular. So if you see the bottom right of the slide here, a typical life cycle of a wind turbine blade, which I think has already been touched upon in previous conversations. We've got the raw materials leading to the manufacture of the blades, and obviously you've got the operation and maintenance phase. Then we've got end of life strategies, where we try and reuse some of that material in new blades or divert it into other sectors, and then we start again. So in terms of blades themselves, they're made from composite materials, so that's a combination of reinforced fibres, polymer matrix, sandwich core, coatings, and metals, and that's illustrated in the top right of the slide here. And whilst turbines have a very good recyclability rate, so if you think about the turbine as a whole, 85 to 90% is recyclable. Blades is a bit of a challenge, and you'll see in the bottom right that wind, at the time of the publication, it was listed as having 66,000 tonnes in 2025, so it was sort of in the range of other industries in there, but of course wind is about to really take off. You know, I've told you about 50 gigawatts in the UK waters, so it's potentially a big problem on the horizon if we don't tackle it properly. So with that in mind, you know, we need to really focus on how we make blades, what materials we use, and how we recycle them. And it's complex because of the complex nature of material that's used in their manufacture. So Michael presented the pyramid in his presentation. So the point I'm trying to make here is that the wind industry is committed to that particular pyramid. So we're trying to minimise disposal and obviously maximise prevention. Just some figures here. In the next 5 years, a lot of the early wind farms are now coming to their end of life. So an estimate was made in 2019 that 15,000 blades will be decommissioned over the next 5 years. 2.5 million tonnes of composite material used in wind energy, and that of course will only get more as the scalability of offshore wind takes off. And then composite materials, they're generally recycled at the moment commercially through cement coal processing. And you see the figure on the bottom right, a lot of the techniques from also, we've got a combination of mechanical grinding and cold processing, but there are other techniques that are available. So for example, solvolysis and microwave pyrolysis are becoming more talked about, more popular ways of recycling blades, but their TRL level is not quite there yet, so there needs to be development and investment in there, because those techniques can actually make the value of the material higher and also more usable than current techniques. So the recommendations from Europe, there was actually two areas that were mentioned in this paper. So the one focused on recycling of existing blades, the other one focused on development of new blade materials. So don't worry if you can't read the right-hand side of the slide, because I've summarised it in the bullets. So essentially, recycling existing blades looked at things like we need studies into the economic viability, we need to demonstrate new solutions, and also we need a cross-sectorial platform, because a lot of the recycling goes into other sectors. It doesn't necessarily stay within the wind sector. And then in terms of new material development, we've got here things like development of new materials, which again we've touched upon in other presentations, facilities to demonstrate how they integrate into wind turbine blade designs, and also focus on the monitoring of the blades during their lifetime, because there's a possibility to increase their lifetime if we're more confident that the fatigue levels aren't as maybe as extreme as thought, and obviously if you can extend the lifetime of the blade, then you have to recycle or dispose less often. And then just on EUREC specific activity, we've been involved in several publications in recent times, so this is just a selection here. So as part of the JIP on circular economy for the wind energy sector, there was an information pack produced about 1 or 2 years ago. We've had a couple of reports as part of our Energy Transition Alliance in the UK on wind turbine blade recycling. And also we're involved in a multi-year programme called SUSWIND. So that's a collaboration between High Value Manufacturing Capital, Crown Estate, Renewable UK and Net Zero Technology Centre. So that program's only just got running in the last 12 months or so. And that's looking at viable ways to recycle blades, explore sustainable materials and processes, and just innovate in future blade designs. So certainly complementary work to the activities that Michael was showing in his last presentation. Okay, so now I'm going to move on to local energy systems, so we'll move back to the sustainability aspect of the presentation. So this is a project that we're involved in at the moment. So the CLUE project is a €6 million project funded by EUREC. Our part is called Scott CLUE, so we've got a demonstration in the UK alongside other demonstrations in Germany, Sweden and Austria. What we're trying to do here is effectively create a multi-vector, multi-energy source local energy community. So these objectives are for the Scott CLUE project and the CLUE project. So objectives 2 and 3, we're working alongside our European partners to try and acquire knowledge and also develop toolkits that we can use to replicate the upscaling of local energy communities. From a Scott CLUE perspective, we're focusing on objectives 1 and 4. So 4 is about using our lead mount turbine, and objective 1 is about trying to implement our web of cells concept, which is illustrated on the right hand side here. This is the demonstration system that we've put in place. So we've got an active management system which is developed by a company called Smarter Grid Solutions, and that's talking to various cells in our project. So we've got a PV and storage cell, two community centres. We've got a wind cell, which is our demonstration turbine. We have a hydrogen cell. We also have some virtual simulated prosumer cells, and all of those cells are using a common network, which is Scottish Power Energy Network, their DSO network. Connecting it, or a key part of this is our demonstration turbine, and this is really useful on this project because of its scale. So it's a 7 megawatt turbine. As you see from the picture there, it's very close to shore. So it's an offshore turbine, but it's very, very close to shore. And that allows us to power 7,500 homes. So very useful for sort of local energy community type projects. And this is a link because effectively what we're doing here is we're combining the CLU project with another project called H105, which is very much focused on hydrogen. So this is a project we're doing with Scottish Gas Networks, and you'll see the lead mast turbines in the bottom left of the illustration there. And that's being used to power an electrolyser, which is being installed this year. And the idea is we've got 2 phases in the project. So the first phase will create a hydrogen network which will power 300 homes. And phase 2, which comes online in a few years' time, will push that up to 1,000 homes and maybe some other local energy users as well. So a very, very groundbreaking project, as I understand, the first 100% hydrogen project for homes, and certainly very exciting for us because we're directly able to show green hydrogen production from an offshore wind turbine. And I think, well, the other point I wanted to mention was that one of the things we're trying to do with the CLU and H105 project is demonstrate if we can provide the local energy community with renewable energy at all times. So not pull in energy from the wider grid network, and there's some of the over the next 6 to 12 months. So just in summary, so on the future energy system, I've demonstrated in this presentation that we're highly reliant on sustainable renewable energy solutions, and as I said, offshore wind is certainly the dominant technology in the UK. The role of hydrogen, so that's really important for connecting all of this offshore wind to the energy system, and green hydrogen is the one I would back. In terms of wind turbine blades, obviously there's a focus on recycling and new materials development. They're the 2 key areas in future blade design, and also our activity on multiple projects, and that will continue. And then finally, on local energy systems projects, CLU and H105, certainly that they're moving into that demonstration phase where the principle of sustainability applies not just to individual components like blades, but also to the wider energy system challenges. Okay, I'll leave it there. Thank you.
Yeah, sorry, Michael was first. You were notified before. No.
Well, thanks for the presentation. Many points also for highlighting green hydrogen. It feels like home to me. So this is the area that I like to talk. So that's why I think about 2 simple questions. So you were talking about wind and hydrogen. Question number 1 is, I guess you're using the PEM electrolysis. Is it on the spot, or do you do the electrolysis somewhere else? And question 2, could you elaborate a bit on the costs of production?
So, first question, we're talking to several electrolyzer developers. Well, PEM is one of the technologies, but it's not necessarily the only. It's not the only technology that we're considering. So I don't. Where it's converted, that is one of the big questions at the moment. So some of the projects we're looking at are suggesting that they would prefer to convert it at the turbine itself, or certainly in almost like an offshore substation type scenario, offshore. Where I think it will go initially is I don't think the demonstrators have got the confidence to do it offshore yet, so I think they'll probably do it onshore initially just to prove the technology, and then they'll, if it makes more sense to do it offshore, then they'll move it offshore as well. Then secondly, the costs. I haven't got the details of the cost analysis that was done on that report, but certainly the point I was trying to make was, as with any sort of emerging technology, it's expensive at the moment, but there's a lot of opportunity with the usual things like economies of scale, optimization to bring that cost down quite significantly.
Thank you.
Yeah, thanks very much. In one of the slides, you talked about recycling of those turbine blades, and you mentioned that recycling is perhaps mainly done. Well, I'm not so familiar with this, but that's mainly done by reusing it in the cement industry, like you mentioned.
I think yeah, I'll just get the slide. Yeah, so I think it's cement co-processing rather than cement industry. I think that's, as I understand it, that's the terminology for the you correct kind of a cement farm in cement. Sorry,
Oh, anyway, so anyway, I don't know exactly what it is, but when you say recycling, there actually is a degrading of materials, or actually are we talking about downsizing?
There is an element of degrading, and I think that's one of the reasons why micropyrolysis is quite attractive, because it doesn't degrade the lines as much, so potentially you could reuse that in a new blade, whereas obviously if you damage the materials, then you're limiting what you can use it for.
Yeah, because that was actually my other question. Indeed, if you look at the other processes which I do not know in this application, then yeah, you're still talking about downsizing a little bit. So actually, it's about deteriorating the quality of the material. Right?
Yeah.
So also the other processes, all policies. I guess could you elaborate a little bit more on what it is? So which extent
Very briefly, maybe some details we will need to clarify later. We have two further questions, and so maybe the last question for Vicky. So, Peter?
Yeah, just a quick question on the hydrogen, following up on Michael's question there earlier. Obviously, if you basically run the whole town on hydrogen and say that's generated by the wind turbine, there's obviously a time where the wind doesn't blow, and obviously that's a big benefit, I guess, of hydrogen, that you can store it and you can utilize it whenever the wind doesn't blow. But if you were to power the entire city or town, how much hydrogen do you plan to store as a buffer? Like, how many days of storage would you require?
It's a good question, and it's one of the things that we're trying to establish at the moment. Another similar thing we're looking at is if you've got a 7 megawatt turbine, what realistically can be the size of the electrolyzer? You know, can it? I don't think it can be 7 megawatts, but can you get up to 5 megawatts, for example? Mm-hmm. So that's a similar thing, and that also leads into how much local storage do you want a fuel cell, for example, attached to the turbine, and that'll help you with things like black start capability as well. So yeah, all these questions are in the mix at the moment, and they are things that we need to answer.
Okay. Yes.
First is related to the recycling rates. Can you tell us something about the new materials that are going to be used for future recyclable nets? That's the first question. And the second one is related to hydrogen production. You mentioned the idea to produce hydrogen, green hydrogen coming from wind offshore wind. So what you're thinking about to deploy the hydrogen production for the electrolyzers plants offshore rather than onshore.
Yeah.
Carry the electricity to the coast and then produce the hydrogen versus the production offshore.
Okay, so I can be very brief with the first answer, because I'm not an expert on the new materials for blades, but I'm quite happy and able to connect you with some of my colleagues to give you more details. Second question, similar to to an earlier question. So we're working with a company called ERM, and they're proposing offshore hydrogen production at the moment. But there's others that are considering onshore. So, for example, arguably we're looking at projects in South Wales, the onshore production. But still, that as to where we will end up. There's pros and cons to both.
Yeah, many thanks. Further, okay, very brief.
Just a very short question. So, in the draft today, it says that the UK households are spending over 500 million to pay for wind turbines being shut down because of lack of storage ability. Do you see that should be able to disappear at some time in the future, and how long do you think it might take?
I think it can certainly be reduced, yeah. And it's a combination of improving storage technologies and also improving connectivity, particularly across the North Sea, for example. How long it will take? It's a good question. I'd like to think if you're looking at 50 gigawatts by 2030, then this kind of issue needs to be tackled a long time.
Many thanks again, Paul. We will continue in our program, and now we will switch to another technology, namely from wind technology to photovoltaics, but still the topics to be discussed are sustainability and the circularity recycling aspects. It's my pleasure to invite Dr. Stefan Abermann from the Austrian Institute of Technology as our next speaker. Stefan will talk about low carbon and eco-design PV products. Here, the status of research and European activities. Stefan, is your floor. You need to share your.
Yes, thank you for the introduction, and also thank you for having me here. So,
We can hear you well, and we can see your presentation. Wonderful.
perfect. Thank you. So, as announced already, today I want to talk about low carbon and eco-design PV products. So, the first part, I want to give a bit of background and summarize the most important scientific questions. So we all know that photovoltaics will play a crucial and central role in the energy transition and the energy system of the future. Global cumulative installations in 2022 reached 1 terawatt, so basically it is a terawatt business. And all future scenarios, massive drug development rate increases in the coming decades. The new EU goals alone intend to bring online over 320 gigawatt of solar photovoltaics by 2025, which is more than 2 times the value that we had in 2020. And they plan to bring online almost 600 gigawatt by 2030. So, depending on the final ambitions, realization scenario given here by the International Energy Agency as stated by policy for full sustainability until 2050, we will need massive resources and production capacities. If we compare photovoltaic power plant, coal-fired one, most of the embodied carbon, namely 60 to 70% of the total life cycle footprint, is represented in the upstream process. And here, the life cycle greenhouse gas emissions are dominated by the raw materials and the underlying manufacturing process. Moreover, according to life cycle assessments, the CO2 footprint is heavily dominated by the energy mix used to produce the modules. For example, using high carbon resources such as Chinese copper may lead to twice as high numbers as compared to Norwegian hydropower, for example. So, crystalline silicon dominate the market with more than 95% share due to its rival efficiency and reliability. So the majority of the CO2 emissions of photovoltaic power plants will stem from these module manufacturing processes. So its production of such modules needs energy-intensive processes, especially the extraction and purification of ingots that account for about 50% of the energy needed. On the other hand, because of the integrated nature of thin-film module production, where the processes can be considered as one single unit process, basically layers are deposited on the glass substrate and then defined into cells and finally modules. This means that the global warming potential of crystalline silicon modules is higher than thin films, as you can see in the graph here. Whereas the balance of system share is more or less the same. So, as stated before, the raw materials are crucial. There are disputed and varying concerns on scarcity issues. And since crystalline silicon will most likely be a dominating technology in the coming decades, we will look at these modules. So, by weight, crystalline silicon PV panels contain about 5% silicon, 1% copper, and less than 0.1% silver and other metals. So the rest comes basically from the glass and the aluminum frame, if it's a frame module. Nevertheless, silver has the highest fraction of global supply, about 50% in 2021. This is the reason why there are regular concerns about the future silver supply. In that sense, innovation helped and will help to dampen the demand growth as it is shown on this graph here from the International Energy Agency. For example, since 2008, silver wafers and reduced probe glass helped to reduce the silicon intensity by more than 50%. And on the other hand, new design and manufacturing processes help to reduce the silver intensity about 80%. Nevertheless, copper may be an issue because it's essential for almost all electricity-related technologies, for example, electric vehicles, also the grid. So could definitely pose a problem in the near future. And also, aluminum has to be taken into account, which is essential for product cells, which is the normally dominating cell technology, also for advancing from content. Finally, technologies such as silicon heterojunction or tandems may lead to new material issues like indium, because these technologies need indium tin oxide, for example. Here is a non-exhaustive list on examples of life cycle assessment and environmental product declaration procedures that I wanted to summarize for you. So there are, regarding LCA, There are several ISO standards. There is, for example, the PEPS Task 12 of the International Energy Agency. Then there are global labels and voluntary agreements, like the Electronic Product Environmental Assessment, that is based on the Sustainable Leadership Standards by the NSF. And on a broader perspective, there is a number of systems that provide guidance for development of product category rules, such as the Product Environmental Footprint category rules, and like the Norwegian or Italian approaches with EPD. The problem or the challenge with all these approaches is that I try to show you in the right picture here that there are differences. All these approaches use different input data, and in that sense it's different to compare them, which also imposes challenges, which procedure should be used and how consistency can be reached here. In the second part, I want to summarize the actual market stimulus and introduce actual European policy instruments that are under development here. So we passed and actual stimulus are already indicating the importance of reducing embodied carbon. In Europe, France was pioneering here that already in 2016 developed two pathways for life cycle assessments of PV modules, one simplified methodology that is more validated. In that sense, or in that action, that also introduced the carbon footprint cap for photovoltaic modules for installations above 100 kilowatt peak that was set to 500 kilogram equivalent CO2 per kilowatt peak for the production. This is a cap that is highly disputed because many think that it was set too high. Moreover, what we see recently, and I will not name names here because I guess you all read the news and will get this information anyway, but there are more and more companies and investors making substantial commitments requiring more ambitious reduction in greenhouse gas emissions along the region. And last but not least, the European Union is currently evaluating the viability of the new policy option to mandate disclosure requirement for the carbon footprint of modules and inverters. This is a more or less two-stage approach. One is on the EU eco-design and actual eco-labeling, which may then be potentially followed by a green public procurement recommendation scheme for public tenders. Let's look a bit more details on that activity. So building on the results of product environmental footprint pilot phase.
Stefan, sorry, you have 2 more minutes. Is that fine?
Pardon?
2 more minutes, please.
Oh, really? Wow, okay. I will accelerate the pitch.
Yes, that will be nice. Thank you.
Okay, so according on the preparatory study, you see here the process that has been done so far. I had the chance to be here involved in this joint issue group and reviewed the result and provided recommendations on the developments via the European Solar Manufacturing Council. And we will have a consultation forum on the 27th of June in Brussels, which will be the next step here. Implementation was originally planned in Q4 2022, but as we all know that this is such policy instruments are lengthy and tricky, we definitely will, I definitely guess expect a delay here. So this is how it should or could look like. Such an energy labeling in the draft, and besides the information on the product itself, the most important information here, as you can see, it's numbers 4, 5, and 6, which basically gives the energy efficiency index in kilowatt hours per year per square meter of module size for the different climate conditions, temperate, coastal, continental, and subtropical arid, and the same thing on the value basis and on the efficiency class basis. So then I'm coming to my last slide. So the key takeaways or the most important challenges and solutions we will have to address is that I hope I have been able to show you that we need more sustainable PV manufacturing, and that this manufacturing needs changes in terms of technology and design. We have to use less critical materials. We have to reduce the silicon loss in the production of silicon modules. We have to reduce the silver. Indium may pose a challenge in the future, but also we have to look at the copper and the aluminum, who is highly demanded also by all the other renewable energy technologies. Finally, increasing efficiency always helps because it reduces the needed module size at the end to have the same amount of energy yield. We have to use the energy and greenhouse gas emissions during production. This can be done, for example, at a technological scale via thinner wafers, but it can be also done via local EU production that makes great use of renewable energy or electricity for production itself. Then we have to design new modules and systems for full circularity that allows us to fully recycle all the materials, but we have to take care here because such changes may also impose trade-offs in other life cycle stages. For example, if we substitute silver via copper, then the reduced lifetime of the module may pose additional challenge. I showed you, in my opinion, it's very important to introduce market and policy instrument to foster all these developments. And finally, which is key, we have to scale up solar workforce in the European Union, and we have to scale up the European industrial manufacturing capacity along the whole value chain to make this production possible and to reduce greenhouse gas emissions. So with that, I thank you. I hope I did not take too long, and yeah, I'm open to questions.
Yeah, many thanks, Stefan. No, you were exactly in time. I wasn't quite sure, you know. But I think it was perfect. If you allow, I have one immediate question. Actually, now as we are seeing the Russian attack on Ukraine, there is current discussions that our dependency on critical raw materials from, let me call them, unfriendly and unstable nations should be reduced. And as we know, it's not only Russia, of course, it's just the most imminent. Is there already impact on your discussions? And yeah, try to keep the answer shorter than my question, you know, but sorry for that.
No, it's a very important question, and it's a very important point. And I mean, anyway, you answered the question already, so you are right. It's very, very important that we get rid of this dependency, not only in terms of oil and gas, but also in terms of the future energy production technologies. And at the moment, we see a huge momentum here, especially regarding local European production, because now obviously, even the last, so to say, share of the people recognize how important that is here.
Many thanks, Stefan. Is there another question from the audience? So if not, many thanks, Stefan, to Austria, and yeah, I hope to see you soon on some EUREC occasions.
Thank you.
Thank you very much. With that, we will proceed to the final presentation of our workshop. The presentation will be held by Dr. Marius Peters from Forschungszentrum Jülich, so the research center based in Jülich, Germany. Marius will talk about towards cradle-to-cradle recycling of PV modules, so a nice complementation of the presentation before. If I remember well, Marius, you're currently in the US. You're welcome. Good morning. No?
Yeah, thank you. Thank you for the introduction. I am addressing you today from Philadelphia, where I am a chair at the PV Specialist Conference. And I'm really a little pressed for time because I have to introduce my plenary speaker at local time 8:30, which is in less than half an hour. So I will unfortunately really have to leave the room in time. Fortunately, I have to say I could not have asked for a better introduction motivation than for the previous talk for the topic that I want to talk about. So here's the outline. Let me see that. So here's the outline of the presentation. First, I want to talk to you a little bit about the fate of photovoltaic modules as we see it today, about module recycling that is established today mostly for silicon photovoltaics, the challenges that I and some of my colleagues see with the current recycling processes, and how we can overcome them and coming towards closed-loop recycling in photovoltaics. And finally, I'm going to present to you some very preliminary results for recycling procedures that we have tried out for perovskite solar cells at my institution. So, unfortunately, I have to say that the fate of most photovoltaic all over the world still looks like I've shown you in this picture. They are ending up in landfill. And that might not be so much of an issue right now because we're dealing with a few thousands, maybe thousands of tons of module waste per year. But future projections with the projected growth of photovoltaics tells us that we in the future will have to deal with millions or even tens of millions of tons of waste. And right now, different regions are dealing differently with these challenges. In the European Union, we have the EEE guideline that demands a certain fraction of module material be collected and another fraction be recycled. The numbers that we show here on the slide are for silicon photovoltaic modules that, as we've seen, have the greatest market share today, but there are certain guidelines in place also for thin film modules. And in other regions, that is handled differently. In the United States, at the moment, there are some states looking into the development of guidelines for recycling. California is the one that is furthest developed there. The approach that the United States are taking is more that they want to have return policies for end-of-life modules to the manufacturers, which, for example, has resulted in First Solar establishing a quite extensive recycling infrastructure already. And in Asia, there is also a lot of activity on recycling, but recycling is seen or considered more of a business opportunity, and developments go there are more in the direction of trying to turn photovoltaic recycling into something that can create value. And at least for the moment, the hope and belief is that business opportunities will help to establish the recycling policies there. So in Europe, as I said, there are we have, I would say, the highest standard in terms of policies for recycling. There are also a number of funded projects that have resulted in some progress and activities on recycling. Probably the most prominent example is the PV Cycle plant in Marseille that's run by PV Cycle, a subsidiary of Veolia. This site, to my knowledge, is the largest institution that is only concerned with the recycling of photovoltaic modules at a capacity of about 4,000 tons a year and a quite astonishing recycling rate of 96% above. However, we have to say when we look at these numbers, it's still a little bit of care and caution we have to take. And I'm going to talk about that in the following slides because the commercial process also in these sites is mostly commercially driven. And that means that the recycling process focuses on value retrieval most of all. And the value retrieval, the materials that generate the greatest value in module recycling are not the one that we have to the greatest amount in the modules. As you can see here on the right, about 40% of the value that you can retrieve from a photovoltaic module is coming out of the silver, which is only actually making a very minute fraction of the weight of the entire module. Other materials that you can recycle and retrieve value from them are aluminum and silicon, and many materials like copper or polymer are only accounting for a very small fraction of the value that can be retrieved from a recycled module. However, glass, for example, while only having a 4% of the value, is making about 2/3 of the weight of a module. So if you want to comply with EU regulations, there is absolutely no way that you cannot recycle glass. We're going to look a little more into glass recycling in a minute. This is a study that I like very much. It was presented by Jan at the last European PV Specialist Conference, and he did a very thorough analysis of the kind of processes and quality that are used for circular recycling. So he took all the components that make up the PV module and gave rates to the recycling processes for different types of architectures, different types of technologies, here for the current technologies and here for future technologies. And as you can see, there's a lot of variation going on. It's quite diverse what kind of recycling processes are available. Only for some of them, we have closed-loop processes like frames and cables. Two is already, the grade 2 also means that we have a good recycling process with a prospect of circularity available here. Grades of 3 to 4 means that is more the standard types of recycling that we have in most places. And for 5 and 6, unfortunately, there are no 6 in this graph, in that there's really no recycling in place yet. And you might be surprised to see grade of 4, which is indicative of a rather bad process for glass in this list. And I want to talk a little bit about why that is the case, because this is an issue that we face in similar form for many of the components that make it into PV modules. So glass is possibly the most prominent recycling product that we have. We know we've done glass recycling for a long time, but the glass recycling in silicon is challenging in that way that we're currently crushing the modules. They are shredded when they are coming to the recycling plant, and that means the glass is intermixed with pieces of metal, with pieces of silicon, and with pieces of EVA, and all of those result in contamination of the glass, which prevents the glass being used for the original purpose, like turning it back into flat glass for photovoltaic modules, or other higher value purposes like photovoltaic containers. The contamination with metals makes it impossible to use this glass for food containers, which means that right now, the glass that we can recycle from photovoltaic module ends up in very low value and low quality applications like aeronautics or some of the other applications. And right now, that might not be too much of an issue because we have a large enough market to absorb the glass coming out of silicon, but this is not going for, silicon photovoltaic modules, but that is not going to stay this way. And the projected growth rates of photovoltaics, you see here, these are some compound annual growth rates that I've pulled out of literature for all kinds of different materials that are used in photovoltaic modules. And the growth rates for the materials, the components, are much smaller than the growth rates that we see for the photovoltaic industry. Which means that the photovoltaic industry is becoming a larger and larger absorber of those materials. It's becoming, it will have a larger and larger market share of this. And one consequence of it, that at one point we were producing so many modules that the recycling of these modules will not be, we cannot absorb the amount of glass that comes out of these modules in any other market for any other application. And the only market that would be able to absorb the volume of glass coming out of solar recycling would be the photovoltaic industry itself, but that means that we have to develop recycling processes into a way that they are circular and can get the products, the recycled glass, out at a similar or higher quality than the initial glass one. So with this, we come towards the ideas that we had towards developing something towards circularity. You can see the circle, it's a bit of an elongated circle in this graph. Here, we're an additional step in between, which is kind of really the issue that we're facing with the recycling in photovoltaic modules, but also for other products. That is that, in principle, we can retrieve any material, any purity that we want. It is just very energetically and capital intensive. And the prohibitive part of this is that if the retrieval of the material requires more energy or capital than the initial production of the material, we won't do it, right? It's going to be newly mined, it's going to be newly produced if it's cheaper and requires that energy. It would also be environmentally less impactful if we do this. So we have to find ways to recycle photovoltaic modules in a way that is not energetically or capital prohibitive, which means that we should concentrate on the reuse of components in photovoltaic modules, or maybe on a material molecular. But if we can do something like this, then we could try to reimagine the recycling or the process for making a recycling modules to be something like this. Right now, the biggest issue, in my opinion, for recycling photovoltaic modules is that modules were never made to be recycled. They were designed to last, and that's kind of a design paradigm for design for eternity. We have no mechanisms included in the modules that make it easy to separate the materials that are included into them. And rather than doing this, what we should do is we should consider modules to be something that lives over several generations, and we should design the modules in a way that we can recycle them and separate the different materials that go into them. We have to account for the fact that modules have to go better. You have to imagine, say, we take the phone, recycle your phone, and if the recycled phone that you get at the end of life would be the exact same phone that you had, might not be happy with this because technology has improved over time, and you might want the newer model. And the same thing is true for photovoltaic modules as well. But we have to recycle in a way that allows the innovation and the improvement in the module technology to be included. So we have started to try and develop a process that can do this for perovskite solar cells. We're really at a very early stage, but this is the kind of procedure that we have established in our own lab. After the production of the perovskite cells, you can see here on this little glass substrates, we're doing a process for dissolution, filtration, and material treatment in order to recreate all the materials so that we can use them in the for the perovskite solar cell. And I want to show you some very initial results for this. This is the process that we established for separating different components in such a cell. You can see an image of the perovskite solar cell. These are the gold contact, and the black is the actual solar cell, it's the structure. We're using a combination of physical and chemical processes to separate all these layers. We peel off the gold here. This works very efficiently, it works very well, but we still see some traces of the gold on the remaining structure. And then we're using different solvents to dissolve all the different layers of the perovskite solar cells. And we do this in the way that the solvents we use are the same solvents we also use for the fabrication of the cell. So we've been able to really separate all these layers very efficiently and with very high quality. And I can show you that we can even do this with retrieving the initial material quality. Right after the process, it doesn't work quite as well. You can see here is an X-ray diffraction pattern that shows you something of the material quality. And this here is the fingerprint that we like for the initial material. After recovery, you see some additional spikes that are indicative of some other phases and impurities that we don't really want. But after a treatment process that we had developed, you see the green line, and the green line is very similar to the blue one. We could also show that for material quality, we can retrieve that. The initial line here is the blue one, and the important bit here is to look at the decay rate. The red curve is the one that we had after recovery, and you can see that the decay rate is a little higher, which means that there's lower quality. But after treatment, ended up with something that had an even slightly better decay rate. So this material is really at a quality stage that we can use it for the production of solars. So with that, I will be the summary of my talk, showing you that well, PV modules can be recycled with great efficiency. We're still far away from a closed-loop recycling for all of that. Recycling is commercially driven. We have, for some components, especially end metals, closed-loop recycling procedures already in place, but for other components, we do not have those. For example, polymers we currently incinerate, and due to the energetic ineffectiveness of the recycling process, that's unfortunately right now the best thing we can do. And I've shown you some very first proposals for designs, how we can turn modules, recycling modules into modules for recycling. Some very first results, how we can recover perovskite solar systems. With that, I thank you for attention, and I don't really have to run the most right away to go and check my head. Thank you.
Okay. Yeah, many thanks, Marius.
Looking forward to hearing from you. Bye. Have a great rest of your conference.
Yes, bye. Bye. Thanks again. Hey, good luck with your moderation. Thank you.
Thank you.
Okay, so no question now, but I think we're all prepared for lunch now. With this, I would like to also thank our online participants of the workshop for joining us. I believe it was interesting, I think a nice number of complementary presentations on the idea of sustainability and recycling on renewable energy technologies. I have to say, let's say, even though I remember that recycling was being discussed in the PV sector since more than 10 years. There's a colleague of mine working on that, or having been involved in projects, and still a lot of questions open, and the same in the wind. So we should connect that part, while running forward, because I can recall that maybe 20 years ago we promised to do that, to do it in a better way than our fossil predecessors, or nuclear, even worse, where they until today have no clue what happens with the waste. So let us be smarter than that. Okay. So with this, I will close the workshop, and you need to stay in the room for a second. Sorry. So bye bye to our online guests, and with that.